Shall we?
Yes.
Okay, so good afternoon, everyone. My name is William, and my supervisor is Christ, and my capstone project is about drone system for intralogistical payload transport. Intralogistical meaning the movement of goods and resources within an enclosed space, and in my example, I used warehouse environment. So before I dive into anything, I fixed this like earlier. Okay, before I dive into anything, I would like to talk about the problem statement. So, warehouse environments are harsh. Warehouse operators have to deal with heavy loads and transportation, which can result in MSD, which stands for musculoskeletal disorder. And not only that, but also they have to position themselves in high places using ladders or scissor forklifts or order pickers. And as we can see here, and with this comes the risks of tripping. And not only in high places do they injure themselves like this, also, as we know, warehouse environments are very large, typically around 20,000 meters squared. And so there's a lot of long distance walking for them. And sometimes the floors can be wet because of cleaning products or oil leaks from heavy machinery. And also, speaking of heavy machinery, sometimes forklifts can be misused and they can cause accidents by bumping into people or other forklifts, and or maybe hitting the rack and boxes fall over, and all these sorts of problems can arise. So this was a sort of motivation for me looking into this. I was thinking maybe what if we can create something that can assist in this environment and make it more sophisticated and advanced. So of course, my project is a drone, so it has propellers, DC motors, ESCs, but then we get to the core control components here. On the left, we have Pixhawk, which is your standard flight controller. It has a built-in accelerometer and gyroscope, and also it has its own built-in PID control algorithm. So whether the drone has a payload or not, it can stabilize the drone and keep it stable in the air. On the right here, we have Raspberry Pi, which is used to control the servos and the camera, which we will go in deeper later on. So here I'm just showing how I stacked these components on top of each other. There's a bit of carpentry we did here. As you can see, it's a structural panel, so they are on top of each other, and this is useful for easily connecting the GPIO pins and the UART pins and etc. And this also helps with maintaining its center of gravity. And also keep in mind here, the texture of the drone is made out of carbon fiber. And the reasoning behind this, as we can see here, I used EduPack from Material Science. And essentially what I did here was set constraints and limits. So from all the materials, we want to make sure the drone has fracture stiffness, so it can handle micro cracks, young modulus, so it's not bendy and it's stiff, and tensile strength, because as we know, the motors have tension forces on the drone as well as the payload, which is pulling from beneath the drone. So we need to make sure all of that are included. And also, as we know, electrical components emit heat. So we need to make sure that the material can withstand the heat. So I added in max service temperature. And with all these constraints and limits, we ended up with this graph here. And what we have here is two sets of family materials. The red one represents composite materials, aka carbon fiber, which I went with. And the black one, the black circles represent polymers. I didn't go with polymers because they tend to be slippery and they lack the frictional grip for a sturdy drone. So here is me connecting the Pixhawk to the computer and back testing it and making sure everything works. As we can see, the gyroscope, as you tilt, it understands its tilt and connecting these with the motors and the and everything, we have a stable drone. Of course, it's not a race drone, so it's not gonna be super fast and tilt. It's a drone made for carrying loads, so it needs to be slow and steady, and maintain its vertical posture. And but that's not it. We need to make this autonomous. So the drone has its camera, and the camera is programmed with Python, and we use OpenCV library, so it can use real-time image processing. And the idea I went with here is that at the bottom right, we can see something called Aruco markers, which the drone, once it detects the Aruco markers, it understands its relative position with respect to the Aruco markers. And with this, we can have the ability to localize the drone on top of the Aruco and land exactly pinpoint specifically on the Aruco. And this is useful in warehouse environments where we are placing boxes specifically from different points. And after all these coding and everything, this subsystem actually managed to work. As we can see, the camera is at the bottom here. And as I move the Aruco around, it's managing to trace it. So it works. Okay, now that the image processing works, let's move on to the gripping mechanism. So, of course, I 3D printed a lot of stuff. I 3D printed the gripper attachment for the servos, as well as a mount here for the GPS. Of course, we need to keep the GPS at a higher level than the other components. So it has a signal, satellite signal reception. And there's also other 3D printed here, like casing for the camera and for the ultrasonic sensor, and also a level here so we can easily put in and put out the battery for recharging. Anyways, back to the servo. So as we can see here on the right, I will look at inside. As we can see, there's a gap here for the slot of the box to fit in, and then the servo latches into it and picks it up. And one key advantageous thing to see here is that the payload's weight doesn't rely on the servo itself. Rather, it relies on the physical statics on the right side here, which is useful so it doesn't damage the servo, and it has more weight. It can hold more weight. And also one more key thing to notice, obviously, as we learned from electricity and magnetism, you should not connect a 22-volt battery directly to a component that only requires 5 volts. So, of course, we used a buck converter, which essentially drops the voltage from 22 to 5 volts. And now all the components have its required healthy amount of voltage, so nothing burns. So, what are the challenges of this project? Well, of course, if there's a drone in an enclosed space, someone might accidentally walk and hit the drone, the propellers, which is very dangerous, and therefore there should be safety precautions there. Also, as I mentioned earlier, the gripping mechanism, it uses like a slot technique. So with a clean surfaced box, it wouldn't work. It needs to have its supported environment where it has a slot attachment, so it can function as a gripping mechanism. And speaking of supported environment, obviously we're also using Aruco markers, so different Arucos should be placed on the warehouse racks or wherever you want, so the drone understands where to go. And speaking of Aruco markers, I want to mention there's thousands of IDs for Aruco, so you can have 1,000 different Arucos, so the drone can have like different options on where to go. Also, finally, as we can see, the drone frame is like really large in compared to the payload, but that's where we go to potential extensions of this project. Obviously, like it's large, but there's a lot of like unnecessary space. Obviously, it can all be compressed into a smaller, thin drone. As we know, the first ever computer was the size of a room, and it evolved to become like even smaller than our phones. So there's definitely potential in that. Also, on the top right here, we can see if this drone were to work, we can definitely pick up even larger payloads, for example, like a furniture-sized payload, and make the two drones synchronized in a way where it can hold together and perform more difficult tasks. And finally, I want to mention that the drone uses rough estimation with the GPS at first, and then it uses the Aruco to specifically drop down. But if we gave the drone a map, its own map of to understand its warehouse and its environment, like pre-installed map, then it would be a safer and more advanced and efficient way for this to work. So I definitely see this as a potential extension. So I want to say thanks to my supervisor, Chris. He helped me out significantly. Also, thanks, Ms. Satanig, for being there for us for all these 4 years. And thank you, everyone here, for being present for my presentation. I have my references here for the statistics of the warehouse injuries and all that. And thank you.
To be honest, I saw a lot of problems here, but
Okay.
I didn't see the solutions for those problems. Particularly working in a closed environment with the drone.
Yeah.
Something that I really would love to see was the implementation of the local navigation system that another guy was telling to be implemented on your drone. Because I believe GPS is not going to work in the warehouses at
Yeah.
any accuracy. For the blade protection, I wanted to see a real protection because that's a solved issue with different kinds of meshes. So instead of warning employees that be careful they're working blades over there, you gotta put some
Like this
protection
protection?
over the blades. Yeah, there's tons of solutions in the market.
Really?
And then, of course, there's a lot of potential extensions for this. You talked about the pre-installed maps or something, but again, so how about there's tons of things that needs to be solved working in a closed environment. You know, like which product should be taken to where, how is it organized, the logistics, because it's like a part of the infrastructure, right? So the warehouse is working, the products are taken from A place to B place. How is that? Is that manual? Is it something that some operator is just taking with the drone A thing, putting in the B place? So, yeah, for me personally, maybe I'm missing something, but I've seen a lot of potential things to work here, and I really wanted to see problems to be solved here.
Yeah, this is like overall a prototype, and it's like more of the idea I'm giving out. Of course, like it doesn't look clean. There's a lot of things that can be much better, but it's like overall the idea that I'm giving out that there is potential to embed drones in warehouses and make them useful for warehouse workers who are going through troubles and hassles.
Yeah.
Well, it's a good piece of automation that can go in a warehouse, but yeah, I personally see a very limited use for this kind of goods delivery within the warehouse. You have to have a standardized cargo container that should match the your latch. You have to have smaller items, much smaller than the drone itself. The weight is very small compared to what we usually see in the warehouses. Actually, we have two engineering solutions here: the cargo latch and the
Aruco.
landing location, which again is a good job.
Thank you.
And one question about you said you implemented some computer vision. Yeah, you are detecting some
Yeah.
some elements, and then is there a loop which is connected to autopilot to the to move towards that object?
Loop? Like what
I
loop?
mean, when you detect something that it is in the right side, then you should go to the right.
Yeah, it localizes. Like it
How you
detects
create it?
and like
Is it implemented in your system?
yeah, I have the code for that. I mean, I already showed how it was working with the camera. All it needs to do.
Computer vision part,
Okay.
with the OpenCL, etc.
Okay.
That part I
Yeah.
understand. But whether there is a connection with autopilot to move it to the center.
Yeah, there is. Now I have the code, but I didn't have a safe environment to test the drone to move on its own. But yes, it would work the way you're saying. Like it would detect Aruko, and it would like move left, right, up, down until it places it exactly in the middle and slowly, gradually.
Okay, but the question is whether you implemented the code that is having the connection with the autopilot to create the right vector of the power to go to the right position after understanding where is the object.
Yes, it's in my paper.
I have a question.
Sure.
Just in passing, you had something there that said standard control system software, or something like that on the left side of the screen early on. These things are just basically a library functions now. You just have like this control system packaging. You just you just input values into it, and it controls the whole thing.
Which part?
Keep on going.
Okay.
The PID, like the PID control.
Okay.
Left
Right
again.
there.
This one?
Yeah.
Okay.
Xbox.
The Pixhawk. Yeah. Okay.
It's just a piece of software and just use it and it just magically works.
No. You need to set it up. Like it needs to study the motors, each motors, and you need to. It has PID, so it needs to keep like running and like the drones till it like stabilizes. That's how it works.
So you don't really have to write that software anymore.
No. It has
It's magically available.
like this only worked. The video, this only worked because I was dealing with the Ardu Pilot software. I was the one setting it up. It wouldn't. You don't just connect it and it works. You have
Well,
to.
I know that, but I mean, you don't have to write all the feedbacks and all this kind of stuff. You just input it, and it just works.
Yeah, mostly it does it by itself. Yeah.
Okay. I just go for the caveman.
Yeah,
days, that's
sure.
So,
And one more small comment. Working on a closed environment would be really important to have rangefinders on all of the sides of the drone for the safety reasons. So if you have a rangefinder, something like ultrasound or can be a laser or anything. So if you have a rangefinder,
There is ultrasonic.
you have rangefinders?
There is ultrasonic, so it can detect like altitude and
No.
its surroundings.
I mean rangeFinders across the
Yeah.
perimeter.
So like it detects like the wall with sound. Yeah.
To avoid collisions.
I have that only facing down, but I can definitely like add more. But for now, there's
Yeah, I mean on the sides
Yeah.
and on the top, so you can, because you're in a closed
Yeah,
environment.
you're right. Absolutely.
But that's an easy thing, so
Yeah.
you can
Yeah.
William, with the current configuration, have you calculated the maximum payload that you can carry with this drone?
Yeah. The math is in the paper. It's around like 5 kilos. But this is just prototype. Like.
Three things. One, they've already mentioned propeller safety. Again, I think you can do a lot. One thing that probably in warehouse environments, again, will become important is noise suppression. These things are going to be very noisy.
Yeah.
And there's, again, solutions, off-the-shelf solutions for these propellers that make way less noise.
propellers,
So that's the other thing. In terms of follow-on, if there's ever going to be a follow-on on this, I would consider working with somebody like CSIE in Armenia, like Astrid Kojumian, or even in the US with Naira's group, because they do some wonders with these drones. What happens is, if you've ever been to an Amazon warehouse, once they put the box on there, the 5 kilograms inside that box, as an example, might be a small object like this in a big box like this.
Yeah. So it bounces
it's
around.
going to go around like this, and it's going to tilt. And if you tilt this and you don't have a control system on it to bring it back, and they have some really sophisticated control systems where you can actually put 4 different size propellers and keep that thing stable. So it'll be a nice follow-on to incorporate some of those things, especially again coming back to the warehouse environment where you don't want this thing banging into a person. But really good,
Oh, thank you.
good stuff.
Much appreciated.
No questions?
No.
Thanks.